guys, in this video we're going to look at Le Chatelier's principle and dynamic equilibria in general. The first question we've got here is quite an easy one, but I picked it because it's an example that comes up quite often. It's all to do with copper sulfate and it being hydrated and not, which we call anhydrous. So without water is anhydrous and with water is hydrated. Let's have a look at this question here. It says the diagram shows how anhydrous copper sulfate can be used to test for water. So remember, this says anhydrous copper sulfate, so it doesn't have any water bonded to it. Now, if we look at the first part, it says what colour change would you expect to see when water is added to copper sulfate? And it's a very straightforward question. We can just use the equation that we've got here. So let's get the pen. And you can see that it starts off white. And then when we add the water, it goes from white to blue. Now for those people taking higher tier, this is something you're going to have to know and remember. And it's well worth having this written down on a flashcard with the colour change, because this comes up quite frequently. Now when this happens, you will see that you get a reversible reaction. We can, if we choose to, dehydrate this copper sulfate here, remove the water and go back to having the white anhydrous copper sulfate from the beginning. The next part says draw a ring around the meaning of this symbol. Well, we just talked about it, haven't we? That means it's a reversible reaction. The reaction can go both ways. Let's have a look at the second part. So this is question 2 and it says bleach is a solution of sodium hypochlorite, NaClO. Chlorine gas is produced when bleach reacts with hydrochloric acid and it gives us the equation. Give the test and result for chlorine gas. Right, the chlorine gas test is damp litmus paper. Litmus paper. And the colour change that you would expect to see is really just the bleaching of the paper. It bleaches white. The paper that is generally blue starts to just turn white. The colour of the blue paper just fades and you get this white staining. So we say that you use damp litmus paper and it bleaches white. Now this next part says the diagram below shows a sealed flask of sodium hypochlorite and hydrochloric acid at equilibria. Explain what equilibrium is reached in this reaction. Now in order to do this question, you need to know the definition of dynamic equilibria. So I'm going to write that here at the side. Dynamic equilibria is when the rate of the forward and reverse reaction are equal. So when the rate of the forward reaction is equal to the rate of the reverse reaction, we say it's in dynamic equilibria. Now the second part of this, which is very important, is it has to happen in a closed system. And this is what we have here, a closed system. Any reaction that takes place in here, nothing can get in and nothing can get out. It's closed off by this bung here in the top of the conical flask. And that's important. So it says explain why equilibrium is reached. Well, it's reached because the rate of the forward reaction is equal to the rate of the reverse reaction. And the one that they're doing here is in a sealed container. And that's it, that's the answer. It's just trying to remember that definition. The rate of the forward reaction is equal to the reverse reaction in the closed system. Okay, let's have a look at the next question. So the stopper in the diagram above is removed and hydrochloric acid is added. The stopper is then replaced. Explain what happens to the equilibria. Well, just to refresh our minds of what that reaction looks like is this here. So the stopper is removed and we add more of this, more hydrochloric acid. Now that will have an effect on the reaction and we call this effect Le Chatelier's. What this scientist did was he understood that whatever conditions you change, the equilibria will try to oppose that change. It will change in such a way to try and minimize it. So let's have a look at this one in particular. This says what's going to happen if we change the amount of hydrochloric acid. Well, if we add more of our reactants, then what will happen is it will try to make more products in order to minimize that change. It will want to balance the reaction out. So the reaction will move to the right and more products will be made. And because they've replaced the stopper, what you're going to find is that a new equilibrium will be reached. So we need to put this down as 4 marks, and that's a lot of marks. So this is what I would write. An increase in HCl would shift equilibria to the right hand side, and more products would be made, or the yield of the products will increase. Either of those statements is fine. And the yield of the products will increase. And what you will find is that the new equilibrium or new equilibrium system will be established. It will go back to being dynamic equilibrium because you've then created that closed system again. Right, let's quickly have a look at the next one. Chlorine gas is also produced when hydrogen chloride decomposes, so when it breaks down. So it's given the reaction here, and it says the forward reaction is endothermic. So this is the forward, and we know that that's endo. Now the reverse reaction will have to be the opposite. So if the forward's endo, the reverse will be exo. And just hopefully remember this, endo is the cool side where it starts to get cold, and exo, well, that's the hot side, that's where the temperature increases. So it's important to remember that. So it says predict the effect of increasing temperature on the amount of chlorine gas produced at equilibrium. Explain your answer using Le Chatelier's principle. Brilliant. So if you increase the temperature, if we make the reaction hotter, it's going to want to cool down. And if you look here at the right, the cool side is the endothermic side. So it's going to move to the right. It's going to move with the endothermic side. And the products, the chlorine in particular, will increase. So we can write that here. The reaction will shift to the endothermic side. And just for clarity, that's the right hand side. And the yield of chlorine gas will increase. I think we've got one more after this. So this one is talking about the increase or the effect of increasing pressure. So here's the reaction again. And pressure can be a tricky one for a lot of people. Increasing pressure will move equilibrium to the side with the fewest moles of gas. Now, just hearing that sounds confusing, but if I show you, hopefully it will be a bit easier. So with increased pressure, and what the reaction will want to do is get to a position with low pressure, and the less gas molecules, that's lower pressure. So let's have a look at how much gas there is. Now pay attention to the state symbols here. Okay, we have to look at each gas. So on the left hand side here we have 2 moles of gas. Okay, 2 molecules of HCl gas, 2 moles of gas. On the right we also have 2 moles of gas. We have 1 hydrogen molecule here and 1 chlorine molecule here, so 2 moles of gas. So in this case, increasing pressure would do nothing to the reaction. So it would effectively speed up the forward just as quickly as it would speed up the reverse. It would have no effect. I'll show you what would happen in a second. I'll change the reaction, we'll have a look at one where it would affect it. So let's have a look at this here then. So to finish this, we would say no effect. And the reason there's no effect is because there's equal number of moles of gas on each side. There is an equal number of moles of gas. And it has to be gas, it can't just be moles. Equal number of moles of gas on each side of the reaction. Right, let's have a look at these 2 other points that I want to make. Let's change this then. Let's do a different reaction. Let's do the Haber process. So this is where we take hydrogen and nitrogen and we make ammonia. So we need to balance this. So 3 lots of 2, that's 6 hydrogens there. 2 times 3 here is 6. 2 times 1 is 2 for the nitrogens, and the molecule of nitrogen makes 2 as well. So we know it's balanced. Now, these are gases. Let's have a look what would happen to this reaction if we increase pressure. So we have on the left-hand side here, we have 3 molecules of hydrogen gas and 1 molecule of nitrogen. So on the left here, we have 4 moles of gas. On the right-hand side, we have 2 molecules of ammonia gas. So we have 2 moles of gas on the right. Now the values are different. So changing pressure will have an effect here. If we increase pressure, it will want to shift to the side with the fewest moles of gas. So increasing pressure will shift the reaction to the right, and the yield of ammonia will increase. If I decrease pressure, it will want to move to the side with the most moles of gas, and we'll have an increased yield of both hydrogen and nitrogen. It's really important as well that you look at these state symbols, because for example, if one of these was a solid, we wouldn't count that in adding up the moles. It's only the moles of gas. Now the last thing I want to share with you is a catalyst. Sometimes, and it's quite a trick question really, it's one that throws students off. If you add a catalyst, let's say to this reaction, it will say, what effect would that have on rate? Now, catalysts speed up the reaction in both sides. It speeds up the rate in both sides, in both directions, but it does not have effect on the position of equilibrium. So it will affect rate, but it will speed up rate in the forward and reverse by equal amounts. So it will not affect equilibrium. And I'll write that here just in case that comes up in another question and you want to remember the answer. So a catalyst speeds up the rate of reaction equally on both sides. Has no effect on the position of equilibrium. So it speeds up the forward reaction by the same amount as it speeds up the rate of the reverse reaction. Okay, that is Le Chateliers in a nutshell. If you've got any questions, maybe from other papers that you need support with, let me know in the comments, I'll answer them. Likewise, if you want to go through anything in more detail, let me know. But until next time, see you soon.